And there's a historical note on this slide, too. So it's his teacher, who you might not know L'Hopital, but you know his teacher probably. One of the Bernoullis. First calculus book, too. Yeah.
So did he say that it was his rule? Yeah.
Most rules are named after people afterward, right? He probably didn't call it his own rule. I don't think people generally don't do that. Usually people come behind and name that. Just because out of arrogance too. Also sometimes publish a method and it's not used very widely, and then once it starts getting used widely, people are like, oh, who came up with this awesome thing? It's not shown to be useful until it starts to be useful, So, also, it's often true that things that are named for people are misnamed for people. It's often true that someone just one generation prior to them actually discovered it, but their use of it popularizes it. So often that's true. So let's talk about it seems weird, but we're gonna jump back in as our last thing of this unit. We're gonna jump back into evaluating some limits from what was that, our second unit, I guess? Unit 2, limits, you remember that? And there's certain limits that we couldn't evaluate in Unit 2. So this is one that we had, our first one that we ever came across that was a little bit of trouble for us, but it wasn't too bad, right? I think you remember how we resolved this. What was the issue before we actually show, I think that you all remember how to resolve this, but what is the issue that needs to be resolved? Yeah. Yeah, you have, in fact, not just division by 0, because if it was strictly just division by 0, then we would be it's undefined and walk away. If it's worse than that, it's something else. Okay, but if it's 1 over x and we're approaching 0, then that's undefined, we would just walk away. There's something more, though, that's happening here that gives us a little bit of pause. It's not just that the denominator is approaching 0. Yeah, you have kind of competing things. If the denominator only approaches 0, then there's just no question we will walk away and say it's undefined, right? We walk away. But if the numerator and the denominator are approaching 0, we have this issue. We're kind of well, what this limit might be depends on kind of the speed at which these two things approach 0. So that's the interesting part. The fact that we could do this by doing this piece of algebra is not that. It's something that you remember, I'm sure, right? Factor takes this stuff out. But this form is called, this 0 over 0 that kind of gives us some unease, is called an indeterminate form. I don't know if we used that word at the time, but it would be an appropriate term to use now, but also then earlier if we want to use it, that's fine. And that's basically the entire subject of what we're going to be looking at today as we look at L'Hopitals. It's a way of kind of helping us deal with indeterminate forms, especially when algebraic approaches like this are not obviously in any clear way available to us. This one we'll do by L'Hopitals, but you can do by algebra too. So this is a good first example. I know you're excited to do limits again. This is a unit. I think we've named the unit applications of the derivative, right? So maybe the derivative will be useful to us here as we evaluate some limits. Notice that when we first talked about limits, we didn't have a discussion of derivatives yet. We're going to circle back now with some derivatives and give you, finally, here it is, L'Hopital's rule. Okay. And what this says is, this is an important suppose at the beginning. We should make sure to underline this. If f of a equals g of a equals 0, that is, in the last case, if the numerator f, we're calling the numerator f of x and the denominator g of x, and if both are 0 at some particular value a, then this follows. And I'll give you a proof here in a second. It's not hard. It fits on the slide. This is a comma, just so you're aware. Sorry, it's not like another prime or anything. Then the limit we desire is supposedly equal to the exact same limit as x approaches a, but of the derivative of the top over the bottom. And that's not a typo. We're not asking you to use the quotient rule or anything like that. It seems like after being so careful to take derivatives with quotients, That is in fact not what we're saying here, though, is it? And here's the pretty quick proof. I'm going to start with the right-hand side and just show that this works. As x approaches a, f prime of x, this is, do you agree that the right side is appearing down here? F prime of x that's the limit as x approaches a of f of x minus f of a over x minus a. That's one of our definitions of the derivative, right? I just put this limit as x approaches a, I just split it out, just for the sake of clarity, but, you know, everything here, for all expressions, x is approaching a. So in fact we have the definition of the derivative on top and the definition of the derivative of the bottom for g. Over here, I've just knocked out the x minus a's. And if it's really, this is the big F, in fact the proof just doesn't work unless f of a and g of a are both 0, which we said in the hypothesis, right? If and only if that's true, then we get the result. Okay? So there's a pretty quick proof of this pretty powerful thing we're about to use. You don't have to know the proof necessarily, but there it is. That's the ticket right there. If you're having trouble, you have an indeterminate form in your life, take the derivative of the top and the bottom, and now try again is all, right? So we'll try that on the example we just did in a second. We'll give people a chance to digest what's on there. But we can't stress enough the importance of the hypothesis. There's some other language there. You can, obviously they have to be differentiable in order to even talk about f prime or g prime.
Why does f of a become 0?
Why does f of a become 0? Because we supposed it, yes. It's part of the hypothesis.
Oh, great, got it.
Yeah, this only applies if when you plug in a in the numerator and the denominator, you get 0 and 0.
Okay.
Yeah. Like the problem we were just working on. Right? What did we get, by the way, on the previous slide when we did our algebra unit 2 style algebra? We got 4, is that right? So let's see that we get the same thing using L'Hopital's on the problem. This time we'll use L'Hopital's to see if we get the same answer. Maybe you've already tried it. Does it work? I don't know. Let's give it a try. So this is the same one, but this time I'm asking you, please try using L'Hopital's. So what does it say? It says if when we plug into to the numerator and the denominator, then and that equals 0, and it does, right? 0 and 0. Then L'Hopital's applies, and so how does that work? What does L'Hopital's say from the last slide? This limit is equal to the limit as x approaches 2 of what? Yeah, f prime, which is 2x on top, supposedly. Again, I know this feels wrong, doesn't it? We just proved the fact that this works, so it's okay. I mean, you can do it. You can do it. But it does feel a little bit weird to be taking a derivative and another derivative on the bottom. And down here, it's just 1. And actually, I think we can plug in 2 now. And do you get 4? I think you get 4. Wonderful. That was painless. It wasn't like painless enough to maybe prove to you that this is like a really great technique and we should do this rather than the algebra though. But yeah.
Oh yeah, I was going to ask why we should use L'Hopital's.
Yeah, like for ones like the one I'm about to give you. Right, okay. So let's before we do anything else, let's verify that it is actually indeterminate. And I'm not saying there wouldn't be like an algebraic way to do this necessarily. Maybe there would be. I don't know. Is that you good? Was that good? Okay. All right, so here's a slightly more interesting problem. Can you please just verify quickly? I don't need you to like write it out necessarily, but can you just verify or plug in by hand, in your head at least, that's indeterminate? Is that 0 over 0? Does it work? 0 plus 1 minus 1 is 0 on top. And if you plug 0 into the bottom, do you get 0 also? So I think we do have the indeterminate form that we've been discussing. I think we do have 0 over 0. Okay? So I think L'Hopital's applies. We just need to take some derivatives here, right? So the derivative, the limit of this thing. So I don't know. Go ahead and try it before I do it here. Tell me what happens. Take a derivative on the top. Take a derivative on the bottom, and tell me if you can plug in 0. Yeah. Well, let's see. I mean, we'll see. Well, maybe on the top it's gonna not be 0. I don't know. We'll try both. That'll be okay. You have it right. But we'll see what happens. Take derivatives. Then we'll talk. Yeah, I'll do the bottom for you. That'd be nice of me. Yeah, you will.
Should we start chaining this into the derivative of that too? That doesn't work.
Does L'Hopital still apply is the only question I have, right? Is the hypothesis met? Is it an indeterminate form still?
Yes.
If so, then yeah is the answer. So we'll see if that works here. So some of you have run into this issue here, I guess. 1 plus x to the negative 1/2 minus 1/2. Is that what that is? Okay. So if you plug in 0 on the bottom, you definitely get 0, as Nick pointed out. And if you plug in 0 on the top, you also get 0, don't you? So this is another indeterminate form. And if this is the question in your life, this is no longer the question in your life. If this is the question in your life, and it's indeterminate, if someone just like walked up to you with this problem, you'd be like, I'm going to use L'Hopital's on that, not knowing that we maybe already did, right, one time. But let's do it again, yeah. We're having so much fun with it. Until we don't have an indeterminate form, or rather, as long as we keep having indeterminate forms, we can keep using it 2 or even 3 times if you needed to. Okay.
If you get undefined and then get done. Let's say it was like 5 then what would you say?
I mean, I think we're gonna get there. That yeah, it could be that the final answer is undefined. Dude, that's okay.
So then what would you write the answer to the one? Just write undefined.
Yeah. Okay. Or the limit does not exist. So are we able to plug in 0 yet? I think so. Right. I like plugging. I know this looks really messy, but if you plug in 0, it's okay because it's 1 to the something. Who cares? So, what do we get? Negative 1/8. Feel free to confirm this by plugging this into your calculator and actually numerically figuring out what. If you plug in 0.0001, do you get something approximately that's close to negative 0.125? Just you could double check if you like. But the point has been made. I think I don't need to even say it. But yeah, of course, L'Hopital's applies. If it still applies, then it can be applied. Yeah.
What's the longest chain of L'Hopital?
I don't think that any of the homework problems actually make you do more than 2. So I can see though. I can see that you want to do more. Yeah. So again, a problem where any out of our algebra tricks from Unit 2 might not have sufficed. Though I'd be interested to know there might be some trick you could pull to get that. I don't know. I have to think harder about that maybe. But yeah, so the note here is that as long as we have an indeterminate form, we can continue to use L'Hopital's. Is that good? Train, you got it? Okay. Everyone else? Good. I think it's a train. Okay. Let's do another one. Again, before you start, let's just verify that this is actually a hard limit problem. Cosine is, yes, it requires you know the cosine. Is it 0 over 0 again?
Yes.
Wonderful. I mean, not wonderful, but kind of wonderful. Okay. You don't. Yes, you do, Bhupesh. I just wanted to share my thoughts with you. That's all. That's all. All right. So yeah, we're gonna. I think we're ready to apply L'Hopital's. It seems to be the trick of the day. So go ahead and do it. You can feel free to beat me to it. What do we get on top? Sine over 1 plus 2x. All right. And then we're having fun with this, right? So maybe we plug in. Maybe we maybe limit as. You want to do it again? cosine x over 2. Was that 1/2? Is that what you get? Wait. Yeah, maybe we are not allowed to do those things. In fact, we get a wrong answer. What should have we done here? Just want you. It'd be easy on the last one because Nicholas was saying, like, this is kind of fun to keep doing it, isn't it? So don't get carried away. Why can't we keep doing L'Hopital's over and over again here? Yeah, Matthew.
Because 1 plus 2x when you plug in 0 does not equal 0. So
Yeah, this is not an indeterminate form. So what is the answer? I mean, yeah, 0 is what we get. Is that right? 0 over 1. So, yeah, so just be careful. The note on this slide comes with the same warning as we've been saying. Provided that L'Hopital still applies, be careful. You can keep using it, but if it doesn't, don't keep using it, okay? All right? Again, feel free to verify any of these numerically on your calculator. Give us, maybe we're just like saying the wrong thing. The answer to that is no. Were the conditions of the theorem actually met? No. Good. Don't be that person. Don't be that person. Nicholas. Okay. What do you think? You like L'Hopital? So far? So far, so good? I will say it seems somewhat limited because it seems to only work with this like f over g case where x approaches a and we have 0 over 0 or something. But there are other indeterminate forms that we'd like to be able to handle besides like these fractions. Are there other hard limits we might encounter? Sure. These are the other indeterminate forms. 0 over 0 is one. That's not on the list. That's the one we've been discussing at length. But also any of these. And you can kind of, let's think, again, please be careful in how you understand these. By these indeterminate forms, I mean, we have a function that's approaching infinity and another function that's approaching infinity. Or here we have a function approaching infinity and a function approaching 0. So neither one of them is infinity or 0 at any given time. But you can imagine why we have kind of, again, we have this like race. Which one's going faster to 0 is what we were talking about before. Here we're asking which one's going faster to infinity. How are they competing together? You can see how we have to resolve that tie. Depends on how fast each one is growing relative to one another. Same thing here. Is this a value that's going to be close to 0 or is this a value that's going to be close to infinity? If you're multiplying like 1,000,000 times 0.001, like who wins as you get closer? This one's getting close. This one is trying to get you close to 0. This function, if it's going close to 0, depending on how fast it's going, might be winning and drawing the whole limit to 0. Right? Or maybe this one's growing faster. Yeah, Babesh? Yeah, again, let's be clear. We have a function that's approaching 1 raised to the power of a function that's raised to a function that's going to infinity. So, I mean, again, like what if we have a number very close to 1, a function that's giving us values that are really close to 1, like 1.001? Well, I think you would agree that then the whole thing should be close to 1. Oh, but wait, hold up. What if I told you it was 1.001 to the like 7 billion? You'd be like, oh, revise my statement. All right, but then it was like, actually this function just got closer. It's 1.0000001. You're like, actually 1 is what I meant. You see how the competition there? Is this close to 1 or is this close to something astronomical? Not sure, because we have to investigate the two functions. Again, it's not about the two numbers. It's about two functions on all these, okay? Hopefully you can see why each one of these would be a competition. Definitely there's a competition going on there. 0 to the 0, again, it's a function approaching 0 and a function approaching 0 up here. So what are the two values that we're competing over maybe here? Somewhere it's going to resolve maybe. This wants to make the whole thing, if a function up here is working very hard to make the exponent 0, it won't be 0, but it's approaching 0. Then it wants to make the value of the expression what? 1. And if this is approaching 0 here really fast, what does it want to approach? The whole thing. It wants the whole thing to approach 0 to the something. It wants to make it to approach 0, right? So this function that's getting close to 0 kind of wants the whole thing to be 0. The exponent, the function up there, wants the whole thing to be 1, right? And then similar competition over here, right? A function approaching 0 up there wants the whole thing to be 1. A function downstairs wants the whole thing, with that infinity, wants the whole thing to be really big, right? So we have to like figure out how to deal with these indeterminate forms, because it seems like L'Hopital's, the way we gave it a minute ago, seems like it only works with 0 over 0. But that's okay. We just need to get all these other ones into that form. 0 over 0 and infinity over infinity both actually work with the way we've just been talking about it, and actually the proof of that is pretty quick. But let's show you one like well, which one is this? I don't want to tell you. Which indeterminate? First of all, realize that this is a hard limit. Tell me which indeterminate form it is, and then let's see if we can get it into a point where we can even use L'Hopital's. Yeah, this looks like it's infinity times. Yeah, this will be going to 0. Sine of 0 is 0. So this looks like it's going to be the indeterminate form. I need my thought bubble. Infinity times 0. All right, so I think I've verified that we are in like this case where I like don't really know what to do. That's okay. I know how to handle this. I'm going to do everything in my power to turn this into a quotient. So, and by doing this, I'd like to actually turn this from this indeterminate form into one of these indeterminate forms. The only hope I have of doing a problem like this is to get it into one of these two forms, just messing around with it using algebra. So, sometimes we might do some strange things to make this happen, like the following. Do you agree that this is in fact the same problem? Yeah?
Yes.
Tell me what indeterminate form we have here. I mean, clearly it's still indeterminate, right? Because it's still the same problem. But it's taken on a slightly different form now. If we consider now the top function f and the bottom function g, we have a new f and g in our lives. Yeah, what do we have? Yeah, this is now the indeterminate form 0 over 0, and life can go on, right? Let's use L'Hopital's now. Go ahead and give it a try here. Limit. What's the derivative on the top? Derivative on the bottom? Do both of those. What is that? Little chain rule actually going on there. Say it again. What? How are we doing? I kind of like that. You want to cancel out that negative 1 over x squared? Yes. So just say yes. Okay. I just would rather have a problem that looks like this. Maybe I don't know. Anyone want to help me with that? What if we need to? That's what happens. It's cosine of 0 basically. Then, right? Isn't it just 1?
Why is it negative 1 over x squared?
The derivative of 1 over x. I did that quickly, sorry. The derivative of 1 over x is the derivative really of x to the negative first, isn't it? By the way, just because we told you so at the beginning of this year, do you remember that the limit yeah, and in fact this limit is the same as the limit as x. Well, I guess it's not perfectly the same, but it is the same question as this. It's very, so the fact that this is 1 shouldn't maybe surprise us. Because we told you that before. In fact, it might be worth establishing that real quickly. Does it work? Does that ye old rule that we talked about early on this year, does that work? Using L'Hopital's? Jeremy, we just said it was 1, but can you prove just quickly, using L'Hopital's at least, that it works? Right, so that establishes that limit from unit 2 that we just kind of threw at you at that time.
That's really useful.
We good on that last one?
You get to fly back.
Okay. let's do another indeterminate form. Again, let's verify, as usual, let's verify that we can't just like plug anything in, that this is actually a hard limit. Let's figure out which indeterminate form it is, and then let's see if we can get it into the indeterminate form we actually want. Let's start by just plugging in 1 everywhere and just verify that what's going on here. 1 over ln 1, that'd be 1 over like 0 as we get close. As x gets close to 1, this then gets close to yeah, 1 over something very close to a positive number 0. Now we aren't sure. I guess we should say maybe from which side we're coming there. Let's assume from the positive side or something. I don't know. If that's the case, then we have infinity here. And if you plug in 1 here, and again, let's assume we're coming to 1 from the right side, then that's 1 over 0 again, or 1 over something very, very positive and close to 0. So I think that'll be, so we kind of have two infinities competing here, don't we? It actually would be the same story if we did it from the left, actually. So that's why maybe we don't have to be too careful about that. It would be a negative infinity plus infinity, and we'd be asking the same competition question. All right, good. Well, then the next thing to say is, so I think we've got it. We figured out. Sorry, I should have put a little bubble around it. There we go. That's the form we're in. Is there a way to get this into the form we like? That stacked form? I don't know. What algebra appeals to you? Talk to your group for just a second and see if you can get this into that form. I mean, really, we're just going to go to any blank we can to make that happen. Yeah.
So how do we turn that into something?
Yeah, I mean, if we're not doing 1 over 0, we're doing 1 over 0 very
Yeah.
So, imagine, what do you think you get from this expression? Did you figure it out? Yeah, find a common denominator. I mean, they really don't have many other moves to make, so I just don't want you to think that, as I do this up here, that I'm like some magician. It's just the only thing that even occurs to me to try, and it is the thing that will work, won't it? So what do we get? X minus 1 minus ln x all over ln x times x minus 1. Did I do that right? Okay. And again, we want to ask the question one more time. Is this indeterminate, and which form does it have then if it's indeterminate? 0 over, yeah, it's definitely 0 over 0, right? You can use something other than top bubbles, but you should definitely keep keep a record of which indeterminate form we currently are in. I think we're ready to use L'Hopital's though. All right, so here we go. Let's take some derivatives. Taking the derivative at the bottom will be fun, right? Up on top, what do we get? 1 minus 1 over x. And on the bottom, we get, here we go. This will be, like I said, this will be the fun part. What do we have to do? Product rule, yeah. So what do we get? So ln x first times the derivative of the second plus second times the derivative of the first. So how about 1 over x times x minus 1? I think that we still have an indeterminate form, and maybe there's something we can do to deal with that. I don't know. I might take a derivative again. I might multiply this out just for the sake of. But it might be indeterminate again. Yeah. But yeah, if you plug in 1, I think we're still indeterminate. So that's good. I mean, Nick likes this situation, because it gives us an opportunity to practice even more derivatives. We've already done 1 over x a couple times today. We like this one. That'll be 1 over x squared on top. And 1 over x plus 1 over x squared. Yikes, this is not looking that fun. Can we plug in 1 yet? I think we can. I mean, you can simplify that a little bit maybe, but no need. The end result here is not a simplified expression. The end result is me plugging in 1, and I think I can do that right now. What do I get? What do you get? Plug in 1. If you can. 1 over 1 plus 1. Yeah. So I claim the answer is a half. Didn't see that coming, did you? Okay. In the original problem, there's no like 2 lurking or anything. Like that defies my intuition just a little bit. But I don't know. Maybe we need to look at the graph a little bit, see what's going on there numerically, figure this out. But the algebra seems to show and prove that it's 1/2. How do you like this? Does this make you happy? Okay. What else we got for you? Nope, don't want to do that yet. Okay. Let's save something for tomorrow. I only have 1 slide. Suppose it's supposed to take us 2 days, so I maybe got a little excited here. We have 1 more somewhat hard case to deal with. Those power cases. Those power cases we need to deal with. Homework 9 though you should be pretty well set for. Okay.
Yeah, exactly.
Yeah, until you can find the derivative. I like the derivative.
Yeah.
We'll see.